melted
Yes, yes. Metal casting means that we have the raw material and we add it with the temperature. And first, we melt this material, and this material becomes from the solid to the liquid. And then we have usually we use the stand. We use the stand to build the class, to build the model. So there's some we have a mold. We have a mold. Okay, we have a mold there. We have a mold. We put this mold in the sand, and then after some time of this sand settles. After this sand settles, so we can just take the mold away, and then we have a cavity there, cavity in the sand, right? And bigger cavity, based on the shape of the final product. And then we pour this molten material inside. And we pour it, and then after some time, so this is molten material and will solidify. After this guy completely solidified, and then we just break the stand, and then take this guy out. Then we have this is the metal casting, the final product. And for example, the cast iron. Cast iron is usually used this kind of metal casting process to build the cast iron, built based on different shapes. So we know we have molten material, and then we let it cool down and to get the solid material. So this process is called solidification. So here are several important factors for the metal forming process, metal casting process. And first one is the solidification of the metal from its molten state and accompanying the shrinkage. It will shrink. We know that as the temperature increases, it expands. When it is cool down, it will shrink. The flow of molten metal into the mold cavity. This is what I said. We have mold cavity, and heat transfer during solidification and cooling of the metal in the mold. And finally, mold material and its influence on the casting operations. Mold material, definitely mold material. We'll talk about this. What are the commonly used mold materials and how they influence the casting operations. So there are different kinds of the metal casting processes. So different metals. First one is the pure metals. Pure metals have clearly defined melting and freezing points, and solidification takes place at a constant temperature. This is for the pure metals. But the pure metals, we know that pure metals are seldomly used because the pure metals are usually not very, very useful because of the strength or this corrosion resistance, durability. Unlike pure metals, we use alloys. We use alloys. That means basic metal. We have some alloying elements there, so then we can increase the mechanical properties of this basic material. So alloys solidify over a range of temperatures. The reason is that because alloy they usually contain several different elements. And solidification begins when the temperature of the molten metal drops below the liquidus. You know liquidus, right? Liquidus is a curve diagram, phase diagram. Are you taking the material science now? Huh? Sarah, you are taking.
Yeah, college.
No, I'm talking material
science now. No, I've taken it before though.
You already taken this one?
Yeah, I've taken it.
Okay. So liquid below the liquidus, liquids below the liquidus is a curve on the phase diagram. So above this is a curve is called liquid. It is stated as liquid. Below this curve, this is some solid. You have some solid. This is liquidus. This is a liquid, and it's completed when the temperature reaches the solidus. I'm sorry, this should be liquidus. The solidus is become a solid. So within this range, the alloy is mache or pastry, whose combination and states are described by the particular alloy's phase diagram. And we are going to show you a phase diagram to tell you what is the liquid and what is the solid, solidus. What is the liquidus and what is the solidus. So here, this is the solidification of metal. For the solidification of pure metal, is the pure metal. I know that freezing takes place at a constant temperature. And second one, density as a function of time, because the shrinkage occurs. So here is the temperature, definite temperature, and plays a very, very important role. This is called the phase diagram. So this is time. So here is the liquid, and here is the solid, the pure liquid and pure solid. And in between this range, and we have both liquid and solid, right? So here, the cooling of liquid and freezing begins. So this is liquid. I'll come here after some time, and we have a pure liquid. And then, but still the temperature is very high. So we call this, it is continuous. It's continuous, this is the temperature continuous decreasing. So from this point and this point, and even though the temperature does not change, but still we should know that this is the heat, right? The heat is released. You understand, right? So also, the reverse process is that when we melt crystalline material, and even though the temperature at the melting temperature, the temperature remains the same, but what happens? It absorbs the heat. Understand, guys? Same thing here. Temperature is related to the heat, but when the temperature remains constant, still here is the heat release. So this is the cooling, and from liquid to liquid plus solid, and then fully solid, and from to this is the solid. This is the fully solid here, and so after this becomes the fully full solid, and as the time goes, the temperature continues decreasing. So here is the specific density. It's where the specific density is changing, but the mass is conserved. But what happens, guys? The mass is conserved, but the volume decreases, right? As a result, the specific density become bigger or smaller. Mass is conserved, right? If it shrinks, that means specific energy, specific density increases. If it expands, the specific density decreases. So here, shrinkage of liquid, because when liquid becomes the solid, it shrinks. If it shrinks, that means the volume becomes smaller, right? Volumes become smaller, but the mass is conserved. And what will happen to this is the specific density? It becomes bigger. Right? So this shrinkage from here to here, the shrinkage occurs. As a result, so this keeps going. But here, the solidification and shrinkage. This is the time. The time does not change, but the specific density there is a jump here. The solid solutions. So when the previous slide talks about this is a pure metal, but we solid solution. What is the solid solution? What do we define solution as, guys? The solution means that we combine two things together, right? Multiple things together. But here, solid solution also means that we combine two things together, but this time this is solid state. Both of them are in the solid state. So I'm talking about maybe you have multiple of these elements. We have substitutional solid is a solution. But the size of the solid is similar to that of the solvent. And what is solid and what is solvent? Huh? The sugar water. Let's see, give you an example. Sugar water, right? We have a bowl of water. The water will be called solvent, right? Right? And what do we call the sugar? Solid, right? So after this is the solute dissolves completely, we call that thing is a that combination of sugar and this is water, we call solution. Right? The same thing here. So substitution is an impurity. We call it impurity. But this is impurity. Solvent is a majority of these atoms. I say majority of atoms we call A. We have some impurities here, and these impurities they call the substitutional. As the name suggests, this case atom size is almost the same as that's the size of these solvent atoms. If this happens, we call this a substitutional solid solution. This is substitutional solid is kind of impurity. We talk about the impurity, right? Impurity means that the foreign elements or foreign atoms. The foreign atoms means that the atoms coming from outside that are different from the majority of these. This is the material. So interstitial, as the name suggests, interstitial. The impurities atom size is very, very small. Very, very small. One size of the atom, sodium atom is much smaller than that of the solvent atoms. So as a result, these impurities atoms can stay inside the space between the atoms of this is the majority of material. So this is called solvent atoms. The solvent, solute solvent. So this will have the substitutional solid solution and interstitial and solid solutions. You know, this is alloy. So this is alloy. We have different elements because we have different elements here. So two-phase alloys. We talk about this is two-phase alloy. You know the phase, right? How do we define the phase? Yeah, right. Phase means what? So we know water, liquid water, ice, and vapor, and they are the three phases of H2O, right? So phase means that the elements are the same, but at least one physical or chemical the property is different. That is called different phases. For example, H2O has three: liquid water, vapor, and ice. What's the difference between ice and the water, liquid water? The state, the physical, one of the physical property is different. You understand? Phases means that so these guys are made by the same element, but they have at least one different either physical properties or chemical properties. They call the phases. If this material changes from one phase to another as a phase transformation, right? That's phase transformation. So this is a solid solution. This solid solution is one in which two more elements are soluble in a solid state and forming a single homogeneous material in which the alloy elements are uniformly distributed through the solid. So here, so the two-phased alloys. So this is a two-phased alloys. But this one, so this is a schematic illustration of grain boundary, and particle dispersed through the structure of two-phase system. So these are grain. So we have these is a dots there. These dots is the particles dispersed through the structure. The grain represents lead in solid solution of the copper, and the particles are lead at the second phase. This is the second phase. So this is another phase of this is the grains. These are grains. The grains are represent lead in solid solution of the copper, but this is another phase of lead. A B is the two-phase system consisting of two sets of grains. See, they are different colors, and definitely they have different material. The dark and light grains have their own conditions and properties. So this is one phase, is a lighter one. The darker one is another phase. Why? Because I know physically and the color is different. Questions? Okay, can somebody tell me how do we define the phases?
Just the different states of like a material, like your example of water. So like, ice and liquid, things like that.
So different phases. First, these phases must be formed by the same element. And second one is that these phases must have at least one physical or chemical properties different. At least one physical or chemical property is different, and they are different. They are different phases, but the same element. So here is a phase diagram. This is a phase diagram for nickel and copper. For nickel and copper. So here is the percentage. This is 100% copper here. This vertical line. So this vertical line stands for 100% nickel. So from here is in between. And so this is very, very beautiful phase diagram. So these are different combinations between these two. So this is liquidus. And here is the solidus. Liquidus means that above this curve, all liquid. Solidus means that below this curve, all solid. In between, both liquid and solid. Right? We know that liquidus is the curve about which all this material is liquid. And solidus curve is a curve below which we have solid only. In between, we have liquid and solid. So this is a solid solution. This is below this one, below this curve is solid. This is solid solution. So this is a liquid solution. So this is both. So you can hear, okay? So suppose we have 50-50, we have this kind of combination between copper and nickel. If we have the temperature, this is alloy combination. If we lower the temperature at this point, at this temperature, and this line passes is the liquidus, and then we will have liquid and solid. Out this line passes this point, which corresponds to 2280 degree F. So we will only have the solid. You can also see it here. So this is the first here, the first solid. So the sum is a little bit lower than the liquid line. We have little sum, just the sum is a solid, this is liquid. And here we will have more liquid solid. So this still majority is liquid. At this point, we will have nearly all these solid. So this is how we read. This is a fixed error. Yes, are you following me? If you cannot follow me, just ask me, right? But also, I want you to know all these facts. I don't want to go very deep, but I want to know these facts. So this iron, so this is a nickel and copper is very, very good example to illustrate. And this is a soluble solution. So then we talk about this iron and iron carbide. So this one is the most important one. Why was the student, my professor told me this is the most important one, phase diagram, and for this is a mechanical engineering student. Why this is most important? And 30 years ago, majority of the material and we use in industry is steel. But now there is a lot of new materials emerging. So here, right? Can somebody tell me what's the difference between iron and steel? and what condition we call steel, and what condition we call iron.
Carbon. The main difference.
Carbon, yes. So iron means that we only have iron, or it's highly pure. This is the iron. Usually, the pure iron has very few applications because of the mechanical problem. However, and people found that in the iron, if we give some alloying, this is the carbon atoms, and we can substantially enhance the mechanical property of this material, this iron. So they found that right here is a pure, this is the percentage, this is the carbon percentage by weight. And here means that the pure iron, when this carbon equals 0. Now I'm only talking about ordinary steel. I'm not talking about any alloying, any other alloys, only steel. Here is iron, pure iron, which has 0% of carbon. And here is 6.67% of this carbon. So this is iron. Okay, so this is from here to here, and this is still are usable. However, if the carbon, the content keeps increasing, and what will happen is it will not be usable. No, I'm sorry, I should not say that. It will not be used as steels. What will you get? You get paraffin. Right? So here, this is different carbon, and you can see this is liquid, this is liquidus, this is liquid. So this is the liquidus. So this is gamma. Gamma is austenite. Gamma have different phase. These are different phase. This austenite is called gamma. This is a pure gamma. Okay, solid. However, this area is gamma plus liquid. So here is alpha plus gamma. Alpha is ferrite. Ferrite. F-E-R-R-I-T-E. Ferrite. And this is delta is a ferrite. Delta is another ferrite. This alpha is ferrite. So see here is the cementite. Cementite is Fe3C. This is the ferrite from here to here. So this is different percentage. This is very important. So here, first one is iron, the carbon, iron carbide, the phase diagram. So this one is microstructure above and below the eutectoid temperature. Eutectoid temperature is 727. Here, this point for this content only, for this point. Okay, this is the gamma. Gamma is austenite. At this point, we will have ferrite, and this is cementite. This is cementite. We have from here, just if this line passes this temperature, we will have two phases. So this is austenite is one phase, and ferrite is another phase. Cementite is the third phase. You can see this is a phase transformation. So as I said, this diagram, I might ask you to tell me, okay? Tell me, and use your own language to tell me what happened here. And the keyword is phase transformation. And from austenite, we get another two. This is the phases. One is a ferrite, another one is a cementite. Cementite is this. This is a texture. We say this is the phase diagram, phase change. And the texture in casting. So here, this is the three casting structure of metal solidifies in a square mode. This is a square mode. And first one is the pure metal. This is a pure metal, and we prefer the texture as a cool mode wall. This is we know. As the mold wall, as the mold, this is mold, my mold. As the mold wall, the cooling rate is much higher, right? You agree? cooling rate is much higher. So here, this is the finer. This is the atoms, the grains are finer. Note in the middle of the figure that only favorable oriented grains grow away from the mold surface. See? From these grains grow from this mold. This mold. If you put the liquid, this molten material here, so as this is the mold wall, and then the cooling rate will be highest. As a result, here is we have fine grains, but go deeper, and here is this is the oriented, favorably oriented grains. So this is for pure metal. For the B is the solid solution alloys. For solid solution alloys, we can see clearly in the middle we will have equal X zone. But for other four areas, we have different these favorable orientation. Can somebody tell me why? Still the cooling rate, right? Because the cooling rate near this is the mold wall is highest one. And in the center, the point of interest is away from the wall inside, and the smaller the cooling rate. So as a result, in the middle, you will have this almost equal X zones. What is equal X zone? What is equal X? What is equal X? Yes, equal, as the name suggests, equal X means that so this case green looks like a circular shape. Not necessarily perfectly circular, but circular. You can see, so this is the top view, and so this is we just cut it. This is a side view. We just cut it. You can see. So the third one is the structure or obtained by heterogeneous nucleation of grains. So nucleation. So here, this is heterogeneous. So heterogeneous means that it's not homogeneous. So this is also equal X structure. So, but these are different, and then different colors means different grains. So this is the texture in casting. So alloy solidification and alloy. So you talk about this is alloy here. This alloy is a pure metal. So this is alloy element. And so here is the temperature. This is solidus and liquidus. And given any alloy elements content, and you draw a vertical line, and then you can explain and how it changes from liquid and to liquid plus solid and to solid. And you can do this. Okay, so this is the mold wall. As I said, mold wall around the mold wall, the cooling rate is much higher than inside. So that's the reason. So here in the around the mold wall, we usually have this kind of dendrites. So this is vertical, which are vertical to the mold wall. So for the green cast iron, we have different patterns here. So here is this one is a minute of the thorium. The same thing, okay? So 8 minutes, 11. Here is 102 minutes after you pour. This is the molten material inside the mold. So what will happen? You see, it goes this way. So this is suppose this is solid standard salt. It's a tree mold. This mold. The first one is for the green cast iron, and the second one is the carbon steels in sand and chill. This is also the metal. The carbon steel. This is note that difference in the solidification patterns as the carbon content increases. As the carbon content increases, and even you are using the same mold, they are different. For example, for the standard mold, for this one, it looks this way. However, for this content, compound carbon content, they have dendrites, very obvious dendrites. For another one, this is also different from the other one. And for the chill mode, for different contents of the carbons, we have different patterns. So that means the carbon contents plays an important role. Also, definitely different materials will give us different pattern. For example, the green cast iron. This is a green cast iron, and so this is steel. So the cooling rate, as I said, cooling rate plays a very, very important role. And how important it is? So slow cooling rate or long local solidification time, the time is very long, resulting in coarse dendritic this structure. So dendritic is a very long one. With large spacing between the dendrite arms, we call dendrite arms. I guess this is called dendrite. This is dendrite, okay? So this dendrite is also called dendrite arms. We want to see here. This is one dendrite arm, second dendrite arm, and third dendrite arm. We call this called dendrite. Generally speaking, we call dendrite. Each of them are called dendrite arms. If the cooling rate or shorter local solidification times result in finer structure and smaller dendrite arms. So this is what we see near the mold walls, right? As I said, near mold walls, the cooling rate is highest. Why? Because it is much easier and for the heat to be dissipated. In the center, on the contrary, in the center, this is the cooling rate is very low. So the third one, the still higher cooling rate, the structure developed are amorphous without any other crystalline structures. This is amorphous. If higher cooling rate, if the cooling rate is very high, it's amorphous. I give you some new idea. Guys. Have you guys ever heard of bulky metallic glass? Bulky metallic glass. Bulky metallic glass. This guy is first is glass. Whenever you hear glass, what comes into your mind? Clear? So microscopically, what comes into your mind?
Shattering.
Shattering? Okay, so glass means if I look at it in a micro scale, very small scale, and it is amorphous. All these atoms are arranged without any pattern. You agree? The amorphous. The metallic means that this material is the metal. So what is a bulky metallic glass? Bulky metallic glass means that we elevate the temperature, right? And then we use extremely high cooling rate and to treat it. And what will happen? And then the atoms, the metallic atoms, will not have time to arrange. As a result, we will have the glassy structure. This is called bulky metallic glass. Can you just jot down what I talk about? So this is new information, or this is new information. This is one of my research. Yes. So BMG is very, very good. It has very, very beautiful property. It's probably the high energy. This is high elasticity. High elasticity. What does that mean? If I have a ball, this is a floor. One is the common floor. Another floor is made of BMT. If I draw a ball there, the same ball, the ball dropped on the BMG will bounce back and forth about 1,000 times. However, if you draw another ball on another floor, it will bounce about 50 or 60 times. This is not exact, but I want to tell you elasticity, highly elasticity. This is just one major. There are also other major mechanical properties for the BMG. I just want to illustrate and how important it is if we can manually, artificially control the cooling rate, and we can get something that is very, very beautiful. Well,
So did you say it's a metal that was cooled down rapidly?
yeah, metal. This must be a metal, metallic, metal material, elevated temperature until it melts. After some time, cool it down. If you cool the cooling rate is very, very high enough that the metallic atoms do not have time to form any patterns, and then we will have amorphous structure. Amorphous structure is also called glossy structure. Glossy structure. Amorphous means that we don't have any patterns. We don't have any obvious patterns. I want to tell you guys, okay? If I ask you using our words to tell me how the cooling rate plays an important role in the metal casting, and tell me this, and maybe you can tell me something about BMG that I just talked about. The casting structure. Okay, so this is molded wall. This is solid. You can see the solid because the solid is the material that is close to the molded wall is always the first part of material and to solidify. So why? Because the cooling rate is maximum here. So this is columnar dendrite. Columnar dendrite means this is column, this is parallel, and B is equiaxial dendrite. See? In different directions, and C is equiaxial non-dendrite. This is no dendrite. The dendrite means the arm, look like an arm. Equiaxial dendritic, and this equiaxial non-dendritic. Non-dendritic is just as almost. This is no dendrite. Dendrite is arm, just like an arm. Another one is for this is single phase. Or single phase material, and this is two phase material. See, the single phase, this is, I only have one single phase here, but here I have two phases. These are two phases, alpha beta, they are just, this is alternating layers. So this is